3. Okay.
I think I'll let everybody filter in around here. Everybody hear me? All right. Well, I'd like to thank the organizers for inviting me here to talk about exoplanet characterization. It's really been a great meeting so far with a lot of different talks covering disks and debris disks, young disks, planets, all different kinds of planets we'll be talking about today. About 8 years ago, I went to my first IAU meeting. It was an IAU Colloquium 200, which was outside of Nice. And at that meeting, I did not know a single person there. I was a second-year postdoc, and the meeting was on direct imaging of exoplanets. Science and technology. And it was called Science and Technology because there weren't any actual planets imaged yet, and so it was really about what we were going to find. And so that was a really great conference for me. We've passed the point now where we have a lot of directly imaged planets, and of course, a tremendous number of transiting planets. And so today I want to talk a little bit about the kinds of planets that we're characterizing. And so by characterization, of course, that in itself is a huge topic. So I'm mostly going to talk about atmosphere characterization, mass radius characterization, a little bit about dynamics, but the topic in itself could be a whole conference, of course. So this is kind of the realm of characterization I'll be talking about today. So this is a plot of log of planet mass and Jupiter masses. This is log of separation in AU. We've got planets detected from transits in red, radial velocity in blue, microlensing in green, and directly imaged planets in gold as of, I guess, about a week ago. And so in terms of characterization, I mean planets that we can really learn something about their physical properties, not just their minimum mass. Can we detect light from the objects? Can we get spectrum of the objects? Can we say something about their atmospheres? So this really, at least today, mostly leads us to planets far from their parent star that we can directly image, and planets close to their parent star, where we can measure the mass and the radius, or we can also learn something about the atmosphere for transiting planets. So really we'll be talking about mostly some of these objects and a few objects out here. So I just want to frame what we're talking about in terms of characterization. So I spent a fair amount of my time thinking about solar system planets as well. This is a plot I like to show, comparing where we were about 40 years ago for the atmosphere of Jupiter compared to the atmosphere of HD 189733, a pretty well-known transiting planet. What's interesting is that this is the first infrared spectrum of Jupiter taken by Gillette et al. In 1969. And this is a spectrum from about 3 to about 13 microns. And just with this very simple spectrum from over almost 45 years ago, you can learn a lot from Jupiter. This is, of course, before we had any spacecraft that went out to the outer solar system. You can see Jupiter has absorption features due to methane at 3.5 and about 8 microns. You can see Jupiter radiates like a 125 Kelvin black body in the mid-infrared. You can see Jupiter is extremely bright at 5 microns. Jupiter is something like 230 Kelvin for a brightness temperature over here. Another thing you can tell, if you look in detail, is that Jupiter has a temperature inversion. You can actually tell this from a spectrum, in that this methane band at about 8 microns is partially in emission rather than absorption. So you have hot gas on top of cold gas. So just from this spectrum, one planet-wide average spectrum, you can tell methane is the main absorber in the planet's atmosphere. You can understand its effective temperature, and you can tell the planet has a temperature inversion. These are the kinds of things we're trying to do for simple characterization of exoplanets right now as well. So there's a similar spectrum for HD 189733b. This is the planet-to-star flux ratio. It's just the measured quantity for transiting planets often. This is a day-side spectrum of HD 189. And so there's spectra here from about 1.5 to, again, about 15 microns. So the spectral coverage here is quite similar to the spectral coverage here. And we're trying to answer very similar questions. What are the main absorbers in the planet's atmosphere? What is the temperature of the atmosphere? What's the temperature structure? So for this planet over here, the main absorbers are probably CO and water vapor. We think the planet doesn't have a temperature inversion. So and we think we can understand the day-side effective temperature. It's probably about 1,200 degrees. And so I just want to point out that we're kind of about 40 years behind characterization of solar system planets. You could also make a plot like this for characterization of tidal evolution, thinking about the tides of Io, which we first started to understand 30 or 40 years ago, compared to tides of, let's say, 55 Cancri E, a hot rocky planet close to the parent star. And so I really like slides like this because they kind of set the scene for what we're trying to do in our work right now. And so why should we characterize planets? And I think the reason why is that by measuring one, you're not going to understand the properties of the whole. Planets are extremely diverse, and I would actually say they're badly behaved. As astronomers, we like to characterize, like to collect and characterize objects and plot them on diagrams and be able to say something about them. I think what we're going to find is that planets are so diverse that although we can plot them on diagrams, we might need multi-parametric spaces to really understand what's going on. So this is a plot of mass radius diagrams. This is radii in Earth radii in Jupiter radii. They differ by about 11. Mass in Earth masses, mass in Jupiter masses, they differ by about 300. The hot Jupiters are exceptionally diverse. You can have planets that have the same mass that differ in radius by a factor of 2. I'm not really going to talk about that today, but it's an incredibly interesting topic. Jupiter and Saturn differ in mass, different in radius by about a factor of 15%. This is a really important open question, is what's inflating hot Jupiters? I'm not going to talk about that today, but of course it's an interesting question. Certainly down at lower masses too, you can have planets of the same mass differ in radius by a factor of 2 or even 3, which tells you that they're a very different composition. So in terms of mass, radius, and bulk density, there's tremendous diversity as well. These lines of constant bulk density are 0.1, 1, and 10 grams per cubic centimeter. So in terms of all classes of planets, low mass and high mass, there's incredible diversity. We can also look at atmospheres and find even more diversity. This is a plot of the IRAC color, 3.6 to 4.5 microns, versus effective temperature for brown dwarfs and for planets. So M dwarfs are here, L dwarfs are here. These are the T dwarfs over here, and the very coolest Y dwarfs down there. And there's some nice trends. We think we understand these trends in terms of cloud opacity and carbon chemistry. An actual black body is in black, and brown dwarfs are in red. And planets, these are all hot Jupiter planets that are warmed by their parent star. And you can see that in blue, they have similar colors, but they're really kind of all over the map. As of yet, there's no patterns really emerging. So again, I just want to point out the planets are a diverse class. The planets, of course, some of these are around K stars, some are around F stars, some are quite close to the parent star, some are slightly further out. So there's a lot of diversity in terms of the environment that planets find themselves in. So we shouldn't necessarily expect them to follow the same patterns as brown dwarfs. There's also GJ436b, a hot Neptune, which is actually just off the plot on the bottom, which is an interesting object I'll come back to. It doesn't really fit any pattern from brown dwarfs at all. We can also look for badly behaved objects for the directly imaged planets. This is H magnitude versus H minus K. This is a plot that's come up before. We'll see it again. M and L dwarfs are over here. They get cloudier and they go down to the right. These are the cloud-free T dwarfs over here. And we can see that HR8799 planets and 2-mass 1207 kind of fall off the end here. Cloudy objects that have temperatures which, if they were T dwarfs, they'd be over here and they'd be nearly cloud-free. And so we shouldn't necessarily expect planets to behave just like brown dwarfs do by any means. So I have about 25 minutes left. I just want to hit some high points so that we could talk about 100 different topics for exoplanet characterization, but I'm going to talk about 4. So what I want to talk about today are low mass, low density planets. This is really a bonanza in terms of finding these and characterizing these objects. By low mass, low density, I mean things of around 5 to maybe 25 Earth masses that have a bulk density of around 1, the bulk density of water. These things that have volatile-rich atmospheres, volatile-rich envelopes. So not rocky objects, low mass, low density objects. I think we're finding some good evidence that some of these objects have extremely metal-rich atmospheres. I don't mean 5 times solar or even 50 times solar. I mean much higher metallicities than that. We're filling in the mass radius diagram for these objects, one of the things Leslie Rogers will talk about later. There's some diversity in planetary properties. And the 2 planets I want to focus on are GJ436b, which is 22 Earth masses, and GJ1214b, which is 6 Earth masses. These both transit in front of M stars. I want to talk a little bit about the joys of higher spectral resolution with the focus on HR8799 from Keck and also some hot Jupiters from the VLT. So those will be in the second half of the talk as well. And of course, right after me, there's 9 additional talks. There's 41 additional posters. So we have a really huge contingent of exoplanet characterization, from atmospheres to evolution to orbital dynamics. So there's a really good and very large group here at this meeting. So the first thing I want to point out is that I think we have tentative but building evidence that some of these low mass, low density planets, hot Neptunes, hot sub-Neptunes, might have extremely metal-rich atmospheres. So in our solar system, we have Uranus and Neptune. They're about 15 Earth masses, give or take a couple Earth masses. we can look in our atmosphere and we can measure the abundance of carbon in the form of methane. And so the carbon abundance in Uranus and Neptune is about 50 times solar, strongly supersolar. In Jupiter, it's about 5 times solar. But what we'd like to know is, well, what's the abundance of oxygen, nitrogen, these sorts of other molecules? The problem with Uranus and Neptune is that they're so cold. They're about 50 degrees Kelvin. It's quite cold objects. So all these other molecules we'd like to see are condensed into clouds way below the visible atmosphere. There's no way spectroscopically to determine the water abundance in any of the 4 giant planets. And so one of the nice things about young planets, planets close to their parent star, is that all these molecules we'd like to see are there. They're there in the gas phase. So in principle, we can get spectra and determine how abundant they are. So we really have no way of knowing if Uranus and Neptune are 50 times solar in water, 500 times solar. There's just no way of knowing right now. But one of the nice things about GJ436b is that we can start to answer a question for perhaps a similar planet of 22 Earth masses. This is a day-side spectrum of GJ436b from Spitzer. This is the day-side. This is the planet-star flux ratio versus wavelength. And this spectrum is really kind of interesting. It's a cool object. It's about 700 degrees. So you expect essentially all the carbon to be in methane. But what you see in the spectrum is that there's methane absorbs here, but the planet's quite bright here. At 4.5 microns, that's where CO and CO2 both absorb. And you expect there to be very little CO and CO2. But there's actually tremendous amounts of CO and CO2. The planet is so dark here that it's been observed 3 or 4 different times with Spitzer. It's been a non-detection every single time. So the planet actually has a tremendous amount of CO and CO2 that absorb here, and very little methane, which would be absorbing over here. So on this planet, we have what you might say a low CH4 abundance, methane, and a high CO and CO2 abundance. And really the only way people have been able to find to make this work is with for such a cool atmosphere, is an atmosphere that's hundreds of times solar, an atmosphere where hydrogen is perhaps dominant by number, perhaps, but certainly not dominant by mass, an extremely metal-rich atmosphere. And I'll talk about this with regard to another planet next, but this is really compelling evidence in that these channels have been observed several times in a row, and they come back with the same ratio every time. There's very little flux here and a lot of flux over here. Another way to probe the bulk composition of the atmosphere to figure out what the mean molecular weight, to figure out how metal-rich the atmosphere is transmission spectroscopy. This is where planets pass directly in front of their parent star. This is another famous technique. And the thing about transmission spectroscopy is that what you're probing is really this blue region. What's the area of the atmosphere's annulus as it passes in front of the parent star? So you're looking for absorption features in this annulus of atmosphere. And so the bigger the annulus of atmosphere, the more significant your absorption features are going to be. And so this signal, this ratio of the area between the annulus of the atmosphere and the star's area, which is huge, is basically some number times the scale height, our planet divided by our star squared. And so the bigger your scale height, the more puffed up your atmosphere is going to be. And so this is parameterized by the scale height, which is RT over mu g. So the higher the temperature, or the lower the mean molecular weight mu, or the lower the gravity, the more puffed up your atmosphere is going to be, and the larger your scale height. And so this is been suggested by Eliza Miller-Rickey a few years ago. This would be a way to probe the composition of an exoplanet atmosphere. If you have an H2 atmosphere, you naturally have a larger scale height, a more puffed up atmosphere. If you have an atmosphere with a larger mean molecular weight, like 10 or 40, you generally are going to always have, all things being equal, a much smaller scale height, a much more compact atmosphere. This is something we can probe for low-mass transiting planets, where we're not assured they're going to be hydrogen-helium atmospheres. For a hot Jupiter, of course, we know we're going to have hydrogen-helium atmospheres. For a smaller planet of 6 Earth masses, your guess is as good as mine until we actually characterize them. So this is GJ1214b. There's a lot of data on the plot. We'll go through some of it is more constraining than others. This is the planet radius ratio, our planet divided by our star. This is a small planet. It's about 2.7 Earth radii, 6 Earth masses, in front of a small M star. This is the radius ratio versus wavelength. There's IRAC data over here, Hubble data over here, VLT data over here, ground-based K-band data. But the general story is that the transmission spectrum, the radius versus wavelength, is fairly flat. It's much flatter than you would expect for a pure hydrogen-helium atmosphere or a solar composition atmosphere. And so this flat spectrum can be explained either by a higher mean molecular weight atmosphere, which compacts your atmosphere down, or by dramatic cloud opacity, which could obscure the atmosphere that you're seeing. So instead of looking at all the data, we can just look at one data set for an example. This is a nice spectrum from Burnett et al. This is from Wide Field Camera 3, from 3 transits. This is the transit depth, the cross-sectional area ratio versus wavelength. And it's fairly flat. And so in red is a solar composition model atmosphere, large red absorption features, definitely excluded by the data. 50 times solar, something like Uranus and Neptune, orange, definitely excluded by the data. You can go to higher and higher metallicities. You can mix in, let's say, 10% water vapor, 20%, 40%, 100% water vapor. Again, much higher metallicity atmospheres. And you can see what happens is that the atmosphere becomes more and more compacted. The scale height shrinks down. And what you essentially find is that assuming no clouds, this atmosphere is most consistent with these blue curves where the water vapor abundance is at least 40%. And so again, we might be looking at an atmosphere like GJ436b, where there's hydrogen and helium, but although it may dominate by number, it certainly doesn't dominate by mass, and it may not dominate by number either. We can look at this from a theoretical point of view, which is, of course, always dangerous, but we can try to make some progress. So this is 500 planets from population synthesis modeling. So this is a plot I've been working on with Christophe Mordicini. This is planet mass and Earth masses versus what we're calling Z envelope. This is the metals mass fraction in the hydrogen-helium envelope, in the hydrogen-helium atmosphere. And so the solar abundance is, of course, 0.015. And so these are models. These are essentially core accretion models, single planet models forming by core accretion. And essentially what happens, we know this happens in our solar system, is that the planets, when they're young, get bombarded by planetesimals. We don't know how big those planetesimals are, but we can investigate the parameter space. And what you find is that for a Jupiter-mass planet around 300 Earth masses, the general model predicts a Z envelope of about 0.1, and that's about what we find for Jupiter, something like 5 or 6 times solar. But the general trend is that as you go to smaller and smaller planet masses, you get higher and higher values of Z. And the Z's are not small, they're large. And so a 6 Earth mass planet like GJ1214b, there's a tremendous amount of diversity, of course, but numbers on the order of 0.7 for the metals mass fraction may not be that unrealistic. This planet may only have 1% of its mass in hydrogen and helium gas. So if it gets bombarded by planetesimals, it doesn't take a lot of mass of planetesimals to make the atmosphere Z quite high. Some of these very small planets really do not have a lot of hydrogen and helium. So if they eat a lot of metals, their atmospheres can become very metal rich. So to make progress in this, we need more than 2 planets, of course. I mentioned I think we'll have a lot of diversity. Certainly in the low mass end, there's a tremendous amount of diversity. So we can't really expect 2 planets to really tell us about a whole class of objects. So this is a filling in of the mass radius diagram. This is a planet radius and Earth radii, planet mass and Earth masses. We have curves of pure iron, or maximum iron content, pure rock, pure water. These are color-coded by how much flux they get. Cold planets are Earth-like cold, are in purple. Really hot planets are in red. And so GJ1214b is here. GJ436b is here. But recently there's been 2 additional planets that are around bright M stars, and we should be able to characterize them. There's GJ3470b. There'll be talk about this planet later on this morning. That's right over here. It's a hot Uranus. It's a Uranus analog. It almost has the same mass and radius as Uranus. But it's about 600 degrees rather than 50 degrees. There's also HD 97658. This came out on Astro PH just Sunday night. If you haven't written your Hubble Director's Discretionary Time proposal yet, you might be too late. FYI. That sits right over here. It's about 8 Earth masses and 2.3 Earth radii. It's also around an M star. So the planet-to-star radius ratio is probably pretty favorable. So these 2 objects are being characterized or will be characterized, and we can see how their spectra compare to GJ436b and 1214b. I want to mention that GJ436b is important in that we are getting day-side data and transmission spectrum data. The transmission spectrum data can be degenerate with a cloudy atmosphere obscuring your features or a high mean molecular weight. But if you have day-side data and transit data, you can break that degeneracy. So 436b is an important object right now in that we have day-side data indicating a high mean molecular weight atmosphere And the transit data are also, I think, going to show us that as well. I want to switch gears and talk about another system of small planets, and that's Kepler 36. So this is a compact, close-in, multi-planet system. This is Kepler 36b and c. This is a rocky object in a 14-day orbit. This is a hydrogen-helium-dominated fluffy object in a 16-day orbit. And so I want to talk about a little bit why this is an important system for a while as well. This is a pretty faint parent star, so these planets probably can't be characterized by their atmosphere. But they have very well-determined masses and radii, and that's because of strong transit timing variations. So planet B is in a 13.8-day orbit. Planet C is in a 16.2-day orbit. They're very close to a 7 to 6 resonance. I think they have the smallest period ratio of any two known planets. The inner planet has a bulk density of about 7.5. It is a rock iron object under high pressure. The further out object, just behind it, is at 0.8 for the bulk density, grams per cubic centimeter. So these objects essentially formed a very similar environment. They have very similar orbits. They have a density that differs by about a factor of 10. And so this is an interesting system because it's one of many compact Kepler planetary systems, but it's one that we can actually learn a lot about. So this is an interesting plot. I want to talk a little bit about dynamics in my talk today, although that's not really what I work on. This is what people call a river plot. This is a plot of the transit timing variation in hours as a function of transit number. And these planets perturb each other essentially every single orbit. So when one planet transits late, the other one transits early, late and early, vice versa. And so these really strong transit timing variations allow you to get the mass. This is really just a plot of a transit. So this is the planet, the stellar brightness is constant, 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 and the planet blocks it out, and it's constant again. This is really you can think of each one of these being a transit going this way, going this way. And so this system is dynamically so active, we can get very, very excellent constraints on the masses of the planets themselves. And so this system's been quite interesting for a number of reasons. It's two planets on very similar orbits that perhaps formed in a very similar environment that have a density that differ by a factor of 10. And why might this be? So there's been two papers looking at the formation and dynamics of the planets. There's also been a couple papers looking at the evolution of the planets. This is a paper I did with my student Eric Lopez, where we essentially conformed the planets with very similar compositions, 20% hydrogen helium, maybe something like Uranus and Neptune. But because of evaporative mass loss, they both are losing mass as time goes on from the strong XUV heating. The smaller planet has a smaller core, and so it naturally can't hold on to its hydrogen helium as well. And so what we find is we can essentially match the known density difference, this is color-coded by density, by divergent evolutionary pathways from a common starting point, just because the lower mass planet more readily loses its hydrogen helium envelope. So, I hear Bruce McIntosh talking. All right. And so this is a process that's common, we think, to all gas. This is a process we can see happening for hot Jupiters right now. We can see hot Jupiters losing mass. But we also can see in the population of low mass, low density planets that they might be losing mass as well. So in my next few minutes, I want to mention two other topics. One is direct imaging of HR 8799. This is another system where dynamics has really helped us pin down masses. Not from transit timing variations, but in this system, dynamics of the multi-planet system have put much more stringent constraints on the planetary masses than spectrum and evolution models have. So this is a very nice spectrum from Konopacki et al. 2013. This is what I would call a pretty high-resolution spectrum. It's R of about 4,000. So what you can clearly see is that water vapor is absorbing over here. There's no methane absorption at longer wavelengths, and there's a very strong carbon monoxide absorption at about 2.3 microns. And this is a pretty cool object, about 1100 degrees. So all things being equal, from equilibrium chemistry, you would expect there to be a strong methane absorption, but there doesn't seem to be any methane there at all. And one of the things I want to point out, and one of the things that the Konopacki et al. Paper spends a lot of time thinking about, is what's the carbon to oxygen ratio in the planet's atmosphere. And this is a really interesting question because it's been suggested that where planets form in the disk might lead to different carbon to oxygen ratios in the disk. This is a paper by Oberg et al. 2011. I just want to look at the gas, the solid line, the C/O ratio versus distance. Depending on where these ice lines are, depending on where these condensation fronts happen, when you condense out water, you take water out of the gas phase. It's a solid now. And that perhaps can increase your carbon to oxygen ratio. So at least in a very simple-minded perhaps way of looking at this, we might be able to understand something important about planet formation, not just by looking at how massive planets are, but also what they're made of. And so this is just a spectrum with 3 different C to O ratios, and they essentially find a best fit for the carbon to oxygen ratio at about 0.65, for instance. Now, one thing that's important, and there's a poster about this by Jonah Teskey, is that I'm not convinced we actually know the C to O ratio of the parent stars either. But if we can actually pin that down, if we can compare the C to O ratios of parent stars to planets, I think that'll be extremely powerful in terms of finding some additional information about planet formation, rather than just looking at populations as a whole of where planets form. So one of the things we're trying to figure out for this planet, there's a very nice poster by Derek Homeyer looking at this, is that the planets, as I showed earlier on this color magnitude diagram, look quite cloudy. All the objects look cloudy, even though they're cool enough that if they were higher gravity T-dwarfs, they would be cloud-free. And this goes hand in hand with this detection of carbon monoxide and the lack of methane. What we think is happening is that there's mixing in these atmospheres. We can see this in essentially all brown dwarfs. There's mixing from below, and hot CO gas gets mixed up into the upper atmosphere. So that the upper atmosphere of HR8799c has an overabundance of carbon monoxide and very little methane. The same thing happens in T-dwarfs at the same temperature, but the mixing doesn't seem to be as vigorous. And so you can see this in the spectra over here. It says HR8799d. This model from Mark Marley that I'm on as well, this is where methane absorbs. So this model has way too much methane, and that these points from Andrew's schema up here show that there's not this strong absorption feature that's predicted. So one of the things we're seeing, this happened yesterday too. Okay, thanks. Is that we're seeing dredge up from below, where I think we're seeing taller clouds due to more vigorous vertical mixing, making these atmospheres appear cloudier than a T-dwarf model. And we're seeing strong vertical mixing from below, which leads to different abundances than you would expect compared to a T-dwarf. But we've only characterized in the order of a few objects. We really need to characterize a much larger sample size. So I want to talk a little bit more about even higher spectral resolution, not for directly imaged planets, but for close-in giant planets in the last section of my talk. So there's actually not a poster or a talk, I think, about this technique here, but I think it's really going to be powerful in the next few years, so I wanted to mention it. And that is very high-resolution transmission and emission spectroscopy. So this has been done with CRI-RES and the VLT, been pioneered by Snellen et al. For HD 209458b. And the basic idea is actually pretty simple, is that if we're observing a transit, during the first half of the transit, the planet is actually coming slightly towards us. It has some radial velocity. In the second half of the transit, the planet is actually going slightly away from us, so it has some negative radial velocity. And so if you have a very, very high resolution spectrum, around R of 100,000, you can actually see this effect, and you can see molecules in the planet's atmosphere. This is really powerful because a lot of the data we have for hot Jupiters is from Spitzer broadband detections, very, very wide bandpass. So it's often difficult to say much about molecular abundances because you can't actually see the absorption features. You're just seeing a wide bandpass. And so this is a interesting plot. It takes a while to see what's going on. This is just orbital phase. So this is the time of transit is exactly 0. This is transmission spectrum when the planet's passing in front of the parent star. And there's a radial velocity gradient here. This is 3 times the original signal to make, but I think you can clearly see it here. You're seeing a radial velocity change from about minus 15 kilometers per second to about plus 15 kilometers per second during the time of the transit. This is in the transmitted light of the planet's atmosphere. So you can actually measure the radial velocity of the planet, not the star, the planet itself. So it allows you to measure the planetary and stellar masses without measuring the star's radial velocity at all. You also can measure the mixing ratio of carbon monoxide in the planet's atmosphere, which is something you really can't really do from broadband observations. And what's interesting to me and other people here is that there was also a measurement of a 2 kilometer per second blue shift indicating strong day to night winds blowing around the entire planet from day to night. And this 2 kilometers per second is about what people had predicted from dynamical 3D atmosphere models for day to night flow. because we think the planet has a permanent day and a permanent night side. This is just for the transmission spectrum. You could also do this at different orbital phases. And really what's important about this technique is it uses cross-correlation. This is a model spectrum of the planet-to-star flux ratio. This is for if you want to do this for the day side spectrum of the planets, you could do this. This is a model of the planet-star flux ratio of a planetary day side, again, where all these CO lines are shown. And what's interesting about this technique is that you can do it at transits, at secondary eclipse, and also for non-transiting systems. There's a lot of bright, non-transiting hot Jupiter systems. This has been used for Tau Boo. Tau Boo does not transit, but you can actually see Tau Boo's thermal emission. You can see this radial velocity change. So two groups measured the mass of Tau Boo by seeing the Doppler shift of the planet's CO lines. And so this has also been used for 51 Peg B. We now know the mass of 51 Peg B. We now know both these planets have a lot of CO in their atmosphere. Another group has used this for HD 189733 as well. One of the things that's most interesting to me as someone who studies atmospheres is that you can see if the lines are in emission or in absorption. That's interesting thinking back to one of our earlier slides about whether or not hot Jupiters have temperature inversions like Jupiter has. If you can see if the day side has lines in emission, that automatically tells you you have a temperature inversion. If you see lines in absorption, that means you don't have a temperature inversion. So this is really going to be a very powerful technique, I think, in terms of finding molecules in hot Jupiter atmospheres. Now, figuring out what the actual abundance of the molecules are and telling us if we have the temperature structure right. There's a lot of radial velocity hot Jupiters that don't transit, and this technique will allow us, I think, to actually do spectroscopy of a lot of these atmospheres. So I'm really looking forward to that. So I'm at 30 minutes, worked out pretty well. So my final thoughts are that I'm just one person trying to do a good job in a half an hour talking about a lot of different topics. There's 9 talks after me. There's 41 posters. There's really an incredible diversity of work that's being shown here. So I encourage you to go look at all the posters. One of the things we have from Kepler, even though it's not working anymore, is a very large sample size of 2 to 4 Earth radius objects. We know these planets are extremely common. They're much more common than gas giants. We should be finding them around nearby bright stars, and that's definitely going to happen. This is really a growth industry. They're common on relatively close-in orbits, on orbits of tens of days, 50 days. They're very common objects. And small planets around small stars have generally favorable planet-to-star radius ratios, which makes them easier to characterize in transit. I think we should really be optimistic about characterization of directly imaged planets in terms of spectroscopy, understanding thermal evolution, and in initial conditions. One of the things that I think is particularly nice about directly imaged planets is that they're far from their parent star. They're not being bombarded by X-rays, UV. There's no photochemistry to worry about. And so if we want to understand carbon to oxygen ratios in gas giants, I think directly imaged planets are going to be nice targets and that we can get very nice spectra across a wider wavelength range than we can for the hot Jupiters. And just to follow up my last point, higher spectral resolution, especially for hot Jupiters, can really lead to important new insights that you just can't get from broadband photometry. And I'll certainly take any questions. Thanks a lot.
Thank you very much, Jonathan, for a great review. So, questions? Sorry, if you can wait for the magic wandering microphone.
All right, so this question is about clouds and directly imaged planets. And so we showed in our paper that you do need thick clouds to be able to match the HR8799 spectrum, or at least the spectrophotometry. But it appeared that we could get slightly better fits if we made the clouds patchy, and there should be some sort of transition between a thick cloud layer covering the planets and the sort of normal clouds. And so I was wondering about your thoughts about the prospects for identifying this transition and maybe evidence for cloud structure, maybe with phase mapping of exoplanets.
Yeah, so that's a really interesting topic. And there's, as you know, there's been a lot of really nice progress for brown dwarfs at the L to T transition. Those seem to be the objects that are the most variable. So the L dwarfs are cloudy, the T dwarfs are mostly cloud-free. And across this narrow range in effective temperature, there's a very strong transition. And it appears to me that those objects are the most variable, so flux versus time. So we're perhaps seeing a breakup in the cloud layer. And so that should occur for the planets as well. It might be quite difficult to get very nice time series photometry at that sort of contrast, but I certainly think it should happen, probably at a lower effective temperature, but I certainly think from spectra it's a little bit more indirect, but I think if the spectra fits, I'll end up being better for partly cloudy. That would be nice indirect evidence.
Another question? Yes, Mike.
Michael Liu, University of Hawaii. On the C to O measurement for 8799, you implicated our inability to measure C to O in the parent stars. But I wanted to ask about another issue for this in general, is that if you feel the models are up to snuff in terms of their predictions for the C to O, both in terms of a relative sense and also the absolute number.
Yeah, I mean, I think in terms of absorption features due to CO and water, I think the opacity databases are quite good, and so I think we're in pretty good shape. For a cooler object where methane would be the dominant opacity source, I think we're not really there yet, so I would be the most worried about looking at methane absorption features in water vapor. You know, it hasn't really been tried to some degree. I mean, we have a whole sample of hundreds of brown dwarfs, and people have mostly been looking at solar metallicity models, and so I think a starting point before we try to do this in a lot of detail for a few directly imaged planets would be trying to see what we see for brown dwarfs, where we have a lot of very nice spectra across a wide wavelength range. And we should test out how well we think we can do C to O for those objects first, would be what I would suggest.
Okay. Yes?
Hi, Jo Barstow, Oxford. Hi. It's a similar sort of question to the previous one, but from a different sort of perspective. You mentioned that for GJ436, there were indications of a very high metallicity, but presumably that sort of thing, the high CO2 to CH4 ratio, could also occur due to disequilibrium processes. So how conclusively do you think we could determine the metallicity of those objects?
Yeah, so the models I was talking about, so these are models Julianne Moses is doing, and so what she's basically found is that for that particular object, you can get a lot of CO and CO2 in the upper atmosphere due to vertical mixing, but no one can actually get rid of the methane. It's such a cool object, methane should be there, and there's really no indication of methane. And so that's what's driving the modeling towards less and less abundant hydrogen. It's just a way of getting rid of the methane. So that model does include vertical mixing. So both things are there.
And yes, Jay, down here.
Sorry, I have a very naive question. You mentioned you get the metal enrichment in the gas giant atmospheres due to planetesimal accretion. So why don't the heavier elements mix more thoroughly in the planet? Why do they preferentially just stick to the atmosphere?
Well, we believe giant planets are fully convective. And so molecules that are not in clouds, the working assumption is that they're mixed. So the 4 or 5 times solar carbon abundance, that should be the carbon abundance throughout the entire hydrogen-helium envelope. But one of the question is, are they really fully convective? And they probably are, but that's something we might be able to answer with the Juno mission going to Jupiter in a couple of years. But that should be the abundance everywhere throughout the whole envelope, unless the clouds take some out.
Okay, and we'll have one last question down here, please.
If you have a day side and a night side on the planet, which is tidally locked, you have a temperature difference, you have a scalar height difference. Do you expect different abundances or cloud formation processes on the day side and night side?
Yes, that's another reason why hot Jupiters are very rich, but they're maybe too complicated. Yeah, so you definitely expect day to night differences, certainly for clouds. For chemistry, it might be that the chemistry gets homogenized because some of the chemical timescales are fairly slow. But for a cloud condensation, you really should expect, perhaps on the cooler night side, clouds to more readily condense. And so there are not any 3-dimensional circulation models that I'm aware of for hot Jupiters that take into account this cloud effect. But you can imagine lots of interesting effects, like the first half of the transit might probe the leading half versus the trailing, and the temperatures might be different. And so in terms of details, there really could be a lot of rich diversity there.
Okay, let's thank Jonathan again.